Computers are at the foundation of modern society, running everything from calculators to airplanes to the internet. Surely we would be lost without these magnificent machines. But even they have their limitations. Take the classic problem of factoring a very large number, think hundreds of digits, into its relatively large prime factors. Since the factors are themselves huge, your computer requires an enormous amount of steps to arrive at the solution. For sufficiently large numbers, the convergence time of the solution could exceed your lifetime. The difficulty computers have with this operation is the philosophy behind modern cryptography.
So, does that mean your data is safe and sound? Well, not quite. There's a special class of computers called quantum computers, which don't suffer from this drawback. This is because of the way they store memory. On a classical computer, operations are represented by either zeros or ones, while on a quantum computer they can be represented as a superposition of both 0 and 1. We call the bits of a quantum computer qubits. To understand this strange property, we first need to know what a qubit is and what it's made from. A quantum bit, or qubit, is fundamentally a two-state quantum mechanical system, such as the up and down spin states of an electron, or the horizontal and vertical polarizations of a photon.
Take the electron spin system. Imagine an atom whose outermost electron is a lone pair. Now, since electrons have a magnetic dipole moment, like a compass, if we subject an atom to a magnetic field, the electron will orient itself with the direction of the magnetic field. This is called the spin-up state and represents the lowest energy configuration, which we call the zero state. Naturally then, the one state, or spin-down state, is when the electron is oriented against the direction of the magnetic field, since this requires some input of energy to accomplish. Now, if the electron is being measured, then it can only occupy one of these states, which is exactly how a classical bit would behave. But while it isn't being measured, the electron is actually in a superposition of both of these states, with a relative probability assigned to each spin state.
When we have more than one qubit, the qubits are free to interact with each other, and can now form mixed spin states, as well as superpositions of them. The qubits are then said to be entangled with each other. This means that they are now described by a single inseparable state, and that attempting to measure the state of an individual qubit reveals the individual spins of the other entangled qubits, without having to measure them. We can take advantage of this process by sending the qubits through a series of quantum gates, which transform the input state into a new output state, like how a classical logic gate works. The final state measured after going through this circuit is the string of bits representing the solution of the calculation. To see the real power of quantum computing, let's, for simplicity, consider a system of two entangled qubits. There are four distinct spin states, each described by a number. Comparing this to the analogous 2-bit system, which is described by only two numbers, we can see that 2 qubits corresponds to 4 classical bits. In general, n entangled qubits corresponds to 2 to the power of n classical bits. To put this into perspective, a fully entangled 275 qubit quantum computer would correspond to as many classical bits as there are atoms in the observable universe.